We only ask some very basic probability questions. I'm talking basic. Just so that you can see this correspondence between what's upcoming, which is serious business, to a basic probability question. Before we get started, though, there's no quiz this week, right? It's the midterm. Quiz one, you have quiz 1 and quiz 2, and then midterm 1. And then after that is quiz 3 and quiz 4 and midterm 2. And then there's a week that doesn't have any assessments at all, except for a homework. So don't be going and trying to do quiz 3 because you won't know what's any of it. I mean, you would open it up anyways and be like, we didn't cover this. So it's midterm 1, and it just covers everything from weeks 1 through 3. Okay. So obviously you would do the homework 3 before the midterm. The z-score. Let us recall from last week when we were in the ice storm. How did we construct the standard deviation? I believe we would have talked about there's a reason it's called the standard deviation and not just the average deviation, because the average of all the deviations is always 0, no matter what.
It's the square root of the variation.
That's the standard deviation, okay? And so the standard deviation is the square root of the variation. And how did we get that variation?
It was the sum of each variation squared divided by the total minus 1.
You mean deviation. It's the sum of each deviation squared.
Yes.
Okay, you said variation. That's fine.
Sorry, yeah.
It's the sum of each deviation squared. And what was a deviation? What does it mean just in English?
Just the one start point and an end point.
If I'm supposed to be in my lane and I deviate into the ditch, then I'm like 20 feet, like I can measure how far my deviation is, right? So in a sense, it's what you observed, take away what you expected, right? I was expected to be right in the middle of the lane, but I was over here instead, and this difference tells me how far away from my lane I was. And we can interpret the positivity or negativity of this quantity as like being to the left or to the right. If this x value here is bigger than the mean, then it'll be positive, and that positivity would indicate to us that we're above the mean. If I'm getting a negative number here, it's because what I witnessed was below the mean. Okay. And this would be the deviation associated with the ith data point. Here's your attendance code, 396-748. So I'll use this little subscript here, the ith deviation, because each data point is going to have a deviation associated with it. Okay, and S, the square root of variance, is the standard deviation. It's somehow taking the collection of all these deviations and standardizing it, since we can't take the average. And the variance was the tool used to produce that standardization, because we would have squared each of the deviations and, for whatever reason, divided by n minus 1. We'll talk more about that another time. Okay. To understand what a z-score is, we would need a strong understanding of a deviation and the standard deviation. Because the z-score, that's so just like every observation had a deviation, every observation has a z-score as well. The z-score for the ith member of my data set, where I is number 1, number 2, or whatever, would be the ratio between the ith deviation and the standard deviation. You just get a fraction. Sometimes it's bigger than 1, sometimes it's less than 1. What happens if it's exactly 1? What do fractions look like that are equal to 1?
1. Same number over the same number.
It's the same number on the top and bottom. So then you could say what? Here. If I said that this should be the number 1, then it must be the case that, say it.
Deviation is the same as standard deviation.
Yeah, that the point that we're talking about, the ith element of my data set. Here's my data set. It has that number and a bunch of other ones, and then way off here in the list is that one, and then there's some more, and then here's the last one. So I'm talking about this observation. I observe this. This is a bunch of wait times at the drive-thru, and I look at that wait time. It has a deviation. That collection of points yields a standard deviation, and each one of those points is also going to have a z-score defined in this way. And if it was 1, then it would exactly tell us that the deviation of that xi is the same as the standard deviation. Okay. And that ith deviation was the observed value minus the mean, and then when I divide by the standard deviation, okay, so we can write like this, because that's the deviation. Instead of thinking about if this was 1, what if it was 0? What would that mean then?
Xi was 0? Which one was 0? don't see which one.
If this whole thing, you would agree with me, that's a number, that's a number, that's a number. I run it all through my calculator, and I hit equals, and it says 0. What must be true?
1, 0. The numerator 0.
The numerator is 0. If this numerator is 0, go further. What must be the case?
The xi and x bar equals 0. Minus, so it'd be like 3 minus 3 equals 0.
Okay.
So it would be the same number.
They're the same number.
Yeah, there we go.
If it comes out equal to 0, then the thing that I'm observing is the same as the mean. So if that z-score was equal to 1, then our interpretation was that the deviation of that point was the same as the standard deviation. On the other hand, if it came out to be 0, then it meant that the value I'm looking at is the same number as the mean. The z-score is trying to measure something for you, but it's doing so in terms of the standard deviation. Okay? So if the z-score is 1, then it's the same number on the numerator and denominator. If it was 2, then it would say that 2 of these standard deviations, it would say that 2 of these particular deviations is equal to the standard deviation. So let's draw a picture. If this is our normal curve, we recognize this is a normal curve, right? It goes up, goes back down, symmetric. This axis of symmetry, well, first of all, the horizontal axis is the z-axis. That's where the z-scores are. And right in the middle is the z-score of 0. And that was where the observed value was the same as the mean. And look at how tall a potential bar would be. Because remember, these distributions came from having an underlying histogram. There's a histogram that you can't see that mimics the shape of this normal curve. And so it would stand to reason that because it's tall right here, that's where we're getting a lot of the observations. We're seeing a lot of the observations with a z-score of 0 because most of the time, if I observe some value, it'll be reasonably close to the mean. And the difference between that observed value and the mean is going to be pretty close to 0. And if I'm talking about a z-score of 1, then it meant that the deviation that I'm looking at for that particular observation was the same as the standard deviation. this here is one standard deviation, because it goes out to a z-score of 1. If I went out to a z-score of 2, it would be another standard deviation. Because the z-score of 2, if my z-score is 2, then it would have to be the case that it is equal to 2 times that your deviation up top, how can I say this? It would be the case that xi minus x bar over the standard deviation, if that was equal to 2, multiply on both sides by s, it says what? It says that your deviation that you are looking at is 2 s's. It's 2 standard deviations. You get it? If I backtrack and say, oh, well, my z-score was 3 for that observation, well, then you can do the same thing, multiply both sides by s, and then this deviation you are looking at is just 3 of these s's. It's 3 standard deviations. So the z-score simply tells you how many standard deviations away from the mean is your observed value. The z-score describes how many standard deviations away from the mean. It's very bad English, but whatever, you get the picture. And what was it when we had a z-score of 0? It was the observed value is equal to the mean, right? So that's telling you that if I went to some data set and computed its z-score and got 0, and it's right in the middle, the mean lives right in the middle. The mean lives right in the middle, and if I observe this value over here that has a z-score of 2, it's literally 2 standard deviations away from the mean. That's all this has done so far. Okay. We should have an if someone hands you a z-score, then you will know, even if you don't know the standard deviation exactly, you still know how it's computed, and the z-score will tell you how many of those steps you are away from the center of this distribution. Clearly, z-scores could be negative. It goes both directions, right? The z-score will be negative if xi minus x bar is a negative number, right? So if xi minus x bar is negative, it means that this observed value is below the mean, over here, to the left of the mean, below it. So if I had a z-score of -1, then it would say that I am 1 standard deviation below the mean. Okay. How did I know where to draw that line for the standard deviation? Let me show you. here's that normal curve. Oh, we're going to draw so many of these throughout the semester. By the way, there's lots of normal curves. This one is the standard normal curve, because the standard normal curve is the one whose mean is 0 and whose standard deviation is 1. Okay. And this curve, it starts off small, goes up to a maximum, goes back down. And it's all curvy. It's not just straight line segments. There is a spot, 2 spots on this curve where we would say it changes inflection. I have indicated those 2 spots here. They're called inflection points. You can see the inflection between those 2 points readily. It's kind of, if it was a bowl, it'd be upside down. Okay. However, on the other side of those points, if it had to be a bowl, it'd be right side up. That's what we mean by inflection. It's actually the concavity. All in between here, it is concave down. And on the other sides of the inflection points, it is concave up. So you can see where that concavity will change. It changes at the inflection points. And it's sort of astonishing that so this curve, it has like an equation, a mathematical equation. You can go to a graphing utility and type in the equation and get this curve to come out. And then if you look at what the x values are, where those inflection points happen, it's the same as the standard deviation of 1. Or it's the same as a z-score of 1. And if the z-score was 1, then the deviation was the same as the standard deviation. So the standard deviation will always be right underneath the inflection point. Question so far? You know the old adage that you can't compare apples to oranges? That's wrong. Because we're about to. You can do it with a z-score. You could compare 2 things that you would think are incomparable. If I had a farm, and on my farm I grow apples, and I grow oranges, then I take a sample of my apples and find its mean. There would be a corresponding standard deviation associated with that sample of apples. I can also do this, and I also grow oranges, R for orange instead of O. and there is a corresponding standard deviation for that sample of oranges. So I'm just going to make up some numbers, and we'll see what happens. I have like no idea what a typical orange should weigh. Does anyone? I mean, how many grams or whatever? Let's say 60 grams. Okay. So I gathered together a big sample of oranges. No one knows how many because I didn't tell you. And we figured out that it was 60 grams. Okay. And that was for apples. And when I did it for oranges, I've got some particularly healthy orange trees, and I'm getting 100-gram oranges on the average. Puny little apples. Now, my standard deviation for those apples is really tight. These apples are all coming out the same size, pretty much. My standard deviation here would be only 3 grams. Sometimes on the orange trees, though, it varies a lot, and I'm getting a 25-gram range. Okay. And that's the typical scenario in my orchard. And I want to go now to the farmer's market and show off the biggest apple and the biggest orange I had of the season. And my biggest apple came in at an astonishing 125 grams. And my biggest orange came in at it was bigger. It came in at 150 grams. The question then is, which one was bigger, the orange or the apple? And you might be tempted to say, well, this is the apple, or excuse me, this is the orange. And it weighed 150 grams. And your biggest apple is only 125 grams. This one wins. But that's an incomplete perspective, because then you would need to apply that thinking that, well, you can't compare apples to oranges. However, if you get out your z-scores for this biggest apple and biggest orange and find their z-scores, then it will be scores on the very same distribution, assuming that my apples and my oranges are both normally distributed. So since apples aren't oranges, but I still want to compare them to see which one was bigger relative to the population it came from, you would get your z-scores out and compare them, because z-scores you can compare. So the z-score for my largest apple, I'm witnessing that it was 125 grams, right? The average was 60 grams, so it's a big positive number. It's way over the average. And when I divide it by the standard deviation, I'll know how many standard deviations above average it is. And the z-score for this orange it was 150 gram orange and 100 grams on average. And then when I divide it by the standard deviation, I'll know how many standard deviations above the mean that orange really is. Now, 150 minus 100 is just 50. 50 divided by 25 is 2. So the z-score for that orange is 2. That biggest orange I made was only 2 standard deviations above the mean. That's actually not that far. But that dang apple, 125 minus 60 divided by 3, that has a z-score of 21.6. The apple is far and away much, much larger than the orange. Even though the orange is technically weighs more, it didn't do anything astonishing. That orange was only 2 standard deviations above the mean. This one's almost 22 standard deviations above the mean. That's something that's virtually unheard of. That would get me, like in the I mean, they would write a news article about it. That's astonishing. Okay. Because look at how our normal curve is shaped with respect to the standard deviations. Zero, 1, minus 1. And you have to remember that this curve goes on forever and keeps getting closer and closer to that horizontal axis. It never can reach it, but it keeps getting smaller and smaller. And there's an underlying histogram associated. So for me to have an apple with almost a standard deviation of, or almost a z-score of 22, it would be way out the door, way over there, and then all of a sudden there'd be a tiny, very infinitesimally short bar that indicated that, well, this one time you had this huge apple. But all the rest of the time, they're in here. Okay. There are some numbers, some percentages associated with these particular z-scores. And if you ever forgot these numbers, you could always look them back up. It's called the empirical rule. And the 3 numbers are 68, 95, and 99.7. (68% of the time) 68% of the time, you'll get observations within 1 standard deviation. (95% of the time, you'll get observations that are within 2 standard deviations. And then 99.7% of the time. 99.7 is nearly everything. It's only 0.3% away from being all of it. 99.7% of the time, your observation will be within 3 standard deviations. Meaning that for the underlying histogram that we can't see, 99.7% of the time, it's in one of these bars, and not in one of those bars way out at the extremes. $68, $95, $99.7. And look at what I'm shading. I'm shading an area, aren't I? That's an easy one to agree to. Yes, this is an area. It's a 2-dimensional region. So then go ahead and make the correlation between all of this area in green being exactly 99.7% of all the area under the curve from negative infinity to positive infinity. Even though it goes on forever, it does not have infinite area underneath it. You can only have 100% of the area, right? Whatever that area is, it's 100%. And this right here is 99.7% of it. If it was going to have infinite area, then you would still have an infinity of the area here in the tails, even if this was finite. This would actually be like virtually nothing, because you'd still have all the rest of it to go out here. It's called a convergent graph. It approaches the horizontal axis so quickly that we do not have an infinite area underneath it. It is finite. It's 1, in fact. Under the normal curve, under the standard normal curve, with mean 0 and standard deviation 1, the area underneath this curve is 1. And that was shown to be true by one of the Bernoulli brothers. You heard of Bernoulli? There was a whole gang of them. They were all scientists and mathematicians, and one of those brothers figured it out. Okay? And sure enough, that number 1 is equal to this number. They're the same thing, because the percent symbols mean to divide by 100. It's vacuously the number 1. Okay. When we get to next week's material, we would be concerned with doing stuff like, if this was a z-score minus 1.2, we would wonder then, what is this area right here? We're going to have a calculator that's going to help us figure it out. Or maybe we'll do the opposite and we'll say, maybe this area right here was 0.13. Then what would the z-score be that makes that happen? You know what I mean? Okay. That's what's coming in week 4. For this week's assignment, they just have the one z-score question, and in reality, you don't even need to use a z-score to get the answer. When we did apples to oranges, we did need it, but this question is dealing with the very same population. It's question 1. It's about the heights of men at some time in the past. We aren't told when. And you have the tallest person, man. You have the tallest man with this height, and the shortest one with this height. And we're told the mean and the standard deviation. That means we can compute z-scores for each of the tallest and the shortest. And then we're supposed to say which one was more extreme. Well, that just means which one is the furthest from the mean. Or actually, it means which z-score is furthest from 0. But since they're the same mean and standard deviation, all you really need to know is which one was the furthest from the mean. That's why it's not a genuine use of the z-score. But you can do it. It's just like, I can use a sledgehammer to break an egg. So the z-score for the tallest guy, we observe him to be 253 centimeters, but the mean was 176.36 with a standard deviation of 8.14. And the z-score for the shortest guy, it had better be negative, right? Because he's below the mean. He had a height of 57.5 centimeters. Wow, it's barely over half a meter. Take away the very same mean, divided by the very same standard deviation. Well, let's get their z-scores. So, 253 minus 176.36, and then divided by 8.14. I get, something went wrong. 253 minus 176.36 is this, and then that divided by 8.14. I'm getting a z-score of 9.415. When you're doing z-scores, 2 decimals is where it's at. So for me to know what 2 decimals I would need, I'd put 3. Okay. So nearly 9.5 standard deviations above the mean. The shortest guy, 57.5 minus 176.36. That's his deviation, and then divided by 8.14. The shortest guy, was 14.6 standard deviations below the mean. So farther from 0. So the z-score for the tallest man being 9.42, and the z-score for the shortest man being minus 14.60. You don't need to put the 0. The shortest man had the height that was more extreme. We good? Okay, that's z-score. That's the only z-score question that they ask you that's like this. But you need that idea because it permeates everything else that we do for the rest of the course. This association between the z-score, the horizontal axis under the normal curve, and so on. Now, we can switch gears to percentile. I think you might know what a percentile is already, because you may have taken a test, some kind of standardized test, and been told what your percentile score was. It's kind of like a ranking. And it tells you about the percentage of people that scored below you. So if you were at the 95th percentile for the NCLEX, then 95% of other test takers scored worse than you. They scored a lower score. But if you were at the 95th percentile for cholesterol, then 95% of other people have cholesterol scores lower than you. It's always about lower. So sometimes it's good to have a high percentile, sometimes it's bad. So we could say that a value has a percentile of P whenever P% of other, when P% of data points are less than the value. So this value that we're talking about does not have to be one of the data points. Okay? The data points, though, are what we're using. Like, let's say we have collected some sample data. Maybe let's collect 100 pieces of data. Okay? I want to collect 100 systolic blood pressures. I'm going to collect 100 systolic blood pressures, and let's say the lowest one that I got was from someone that was barely alive, and the highest one I got was someone that's ready to die. I don't know. Those seem like extremes? Okay. And then we'd have all the other numbers here in between. And I've got here in this table, it's 10 rows, 10 columns. 10 rows and 10 columns, so there's 100 data. I have 100 data points, and they're sorted in order. And it happens to be the case that 120, that there is a data point 120, and it is, like I could label all these. This one was in the first position. This one was in the 100th position, right? And it happens to be the case that this 120 was in the, let's say, 40th position. Okay? Now, the very next number after the 120, let's say, was 122. It's in the 41st position. If it was going to be in the 40th position, it should have been down here, but you forgive me for that. Right? Because they all have 10. Okay. Now, here comes your patient. Here comes your patient, Alice, and her value is 121. What is her percentile rank? Well, we would want to know what percentage of the data points are underneath this or less than this number. And since there's a total of 100 numbers, and since these are all sorted in order, then numbers 1 through 40 are less than Alice. Right? The first 40 numbers on this list are less than 121. True or false?
Sure.
You agree, Jan?
Less than.
Less than 121. Here's our patient. These go in increasing order. That's why it started low, wound up big, and this is in the middle. It's always increasing. So every one of those numbers up to here, all of those numbers are either 120 or smaller. The first 40 numbers are either 120 or a smaller number. Then 121 would fit right here in between these two data points. And that would mean to us that 40 out of 100 were less than 121. Right? 40 out of 100 is 40%. So then that means that this 121 is at the 40th percentile. Make sense? Well, we don't have 100 data points for this question. They've only given us 50 data points. And they want the percentile corresponding to this value, 0.84. So I can look at all these data points. Okay. Now it turns out that 0.84 is one of the data points. Okay, but that's not required. And there's 50 numbers here, and they're all increasing, right? And how many of them are less than 0.84? There's 10 per row and 5 rows. 9. 9 of them are less than 0.84. 9 out of
50.
9 out of 50 is 18%. So then 0.84 is at the 18th percentile. Now they have us do it again. Find the percentile corresponding to this value, 1.45. Okay. My 1.45, that's way down here. Then I'm curious about how many numbers were less than 1.45. So you have the first 4 rows, that's 40 numbers. And then 46, right? 46 numbers were less than 1.45, and that's 46 out of 50. That's 92%. So that value, 1.45, is at the 92nd percentile. Okay, and then they want to switch it on you. Now there's some number that's at the 40th percentile. Why would I say 40th percentile? That's what this P sub 40 means. P sub 40 is a number such that 40% of these data points are less than that number. How can I express this in a little equation here? So there's some amount of these numbers, let's call it n. N many of those data points out of 50 total would need to give me 40%. You solve it for n. 40% of 50. 40% of 50 is 20. Twenty is not the answer. 20 is the place to go look in the table. Because if I go over here to the 20th number, here's the 20th number. Okay. I can't say my answer is 1.10 because if I typed in 1.10, then I wouldn't have 20 numbers less than 1.10. Right? I need to have, at the very least, 20% of the numbers less than 1.10. If I were to put in 1.10, I'd only have 19 less than it. Okay, well, there's a problem here, because the 21st number is also 1.10. So no matter if so actually it will work. Actually, that fixes our problem. Wait a second. So I'll tell you, the definition of percentile is not standardized everywhere in the world, and the author of this book changed it from one edition to the next, and we're on that next edition. And I think the change was in the right direction. It's just that I had gotten used to doing it the wrong way, like they did in the older edition. We have the correct definition. It must be less than, strictly less than, because it used to be less than or equal to. And under that old definition, you could just put in 1.10 and be done. But now we have to think. So, so my formula here has given me the clue to look around the 20th position. However, if I typed in 1.10, referencing that one, while technically there are 20 numbers in the list here before that 21st number, not all of those numbers are less than 1.10. So I'm reasonably confident we would have to go to here. Now, it is in the 22nd position out of 50. So one could argue that 1.11, since it puts not 22 numbers, sorry, it puts 21 numbers below it, that it would be at the 42nd percentile. And that would be true. But because of this repeat here, then I would claim that on this data set, the 42nd percentile is the same as the 40th percentile. Because it stops increasing right there for a minute and just stays flat at 1.40. So I'm going to type in 1.11. So it's not enough to just figure out which position to look at, and it's also not enough to simply go to the next one. Even though I got 20 for n, it was insufficient for me to just go to number 21 and say this is the answer. It also had to be bigger than 1.10. So a better strategy is go to the 20th position and then keep going until you get to the next number that's bigger than the one in the 20th position. Here they want the 75th percentile. Now this will be an even more interesting problem because n won't be an integer. There is some number of data points out of these 50 that would give me 75%. Well, that's just 75% of 50, which should be 62.5. No, that's dumb. It should be 37.5. Let me make sure. Yeah. So I'll just go over to the 37.5 position, right? Now, they come in discrete values. So should I go to the 37th position or to the 38th position, do you think?
38,
Why?
35 is bigger.
Yeah. If I went to the 37th position, then I would be coming back here and saying 37 over 50. It wouldn't be 75%, it'd be less than 75%. So you have to round up. Even if that said 37.1, it won't, but even if it did, I would always round up. When you're doing this percentile calculation, you would always have to round up to the next one in order to get to meet that definition of the percentile being the data points below it. So the 38th number is right here. 10, 20, 30. That's number 40, 39, 38. $1.34. That's number 38. And so 1.31 is number 37. 1.34 is number 38. Can I just put 1.34 as my answer? What percentage of data points are below the 1.34? You would have 37 data points out of 50. That's 74% of the data points. That's not 75%. So I have to go up to this one. Now I have got 38 data points under the 1.35. 38 out of 50 is a little bit bigger than 75%. It's 76%. But we always have to err up with percentiles, not down. So it's better to be at 76% than 74. Don't read all this, it's not worth your time. 10, 20, 30, 40, 39. So there's 38 numbers. That's 76%. So there's another strategy that I didn't think that they used in the new edition, where you would look at these two numbers together and like take their average, 134.5. But I don't think that that's what, I don't remember them doing that last semester. Let me just think for a second. So 134.5 would be in the same boat as 135, because it would also put 38 numbers underneath 1.345. And that hint, or whatever you want to call it, started off by trying to say, with a little reminder of something that they claim is true, but is actually not exactly correct, that here's what they claim is true. Well, you don't even know what the quartiles are yet, so, because that comes after these problems. If I take a data set, I can break it up into 4 pieces, 4 quarters. The bottom 25%, the next 25%, and then 2 more chunks of 25%, just like there's 4 quarters in a dollar. And those spots where you break it are the quartiles, Q1, Q2, Q3. If I broke it right in half at Q2, that is the median. And you could argue that Q1 is either exactly the same or reasonably close to P25. And the reason that they would not be identical, it just comes from the manner in which percentiles are calculated versus quartiles. And I find it peculiar here that they are asking me about P75, and then also had that in their hint, because I don't remember that from last semester either. So are they borrowing from the future and instead want the quartile? Well, the Q3 is just the median of the top 50% of the data. So if I look at the top 25 numbers and found its median, that's Q3. So here's the bottom 25%, and then here is the, bottom 50%. Here's the bottom 50%, and here's the top 50%. And then Q3 would be the median of this top 50%. And since there's 25 numbers there, there will be a number right in the middle. You'll have 12 on each side, 12 and 12, and then 1 in the middle, that's 25. So 12 numbers up, 1, 2, 3, 4, 5, and then that's number 12, and then so this would be the one right in the middle. That, without a doubt, is Q3. It's the median of just the upper half of the data.
I think they So I've answered the questions and I had to do it over.
Uh-huh.
They want you to just round 37.5 to 38 and put in the 38th. So what was that, 1.3?
Yeah. What's the problem with that in terms of the definition of percentile?
38 is bigger than,
How many, if this is going to be the answer that they're wanting, probably is. How many numbers are less than it?
thirty-seven.
37 out of 50. That's 60, or excuse me, 74%. And that's the problem. They contradict themselves. If they wanted Q3, they should have just asked for Q3, because this is not necessarily true by the definition of the percentile. If you want that to be the same, then you have to go back and change your definition to say less than or equal to. And that is not how we got the right answer on the previous questions. We used strictly less than. That's why we always had to go to the next one. So I'd have to do some more investigating to see if this question is always going to be one of the quartiles that they're really wanting, and write them a letter, just like the stuff from week 1. So it's probably 1.34. Let's check it out. If it ain't 1.34, then it'd be 1.345, like we said a minute ago. That would be the only other choices. 1.345 is probably the better choice, because it's not 1.35. It would be right here in between these two numbers, right? It'd be right here in between. It would still put 38 data points below it, but it wouldn't be all the way up to 1.35. So like I said, there are all these different ways to do it. No one agrees on it. And that's how it is. I wonder if I did a similar question, if it's going to give me like P25 or P50. I just did P75 again. What is it on y'all's?
mine was 25.
25? It wants the quartile. It's operating under the assumption that all of these equalities up here at the top really are equal, but they aren't. They're close, but they're not exactly the same. All right. All right, it is nearly 2 o'clock. That should wrap it up for percentile stuff. Up next would be the 5-number summary and the box plot. We'll do that when we come back from break, and then we'll do the probability stuff, and we'll be done. Well, after having talked about quartiles already, then we are primed for this next question. In fact, you would already know the answers, for the most part. The 5-number summary, as the name implies, is just 5 numbers that summarizes your whole data set. It is the minimum Q1, Q2, Q3, and the maximum. It breaks it up into 4 chunks. All the numbers here are the first chunk, and then all the numbers here are the second, and then the third chunk, and then the fourth chunk. It breaks it up into the quartiles. Q2 has another name. It is the median. Okay, well, and like we said, to get Q1, I just need to look at the median of the lowest 50%. And to get Q3, I'd look at the median of the upper 50%. Well, this here is 20 numbers. They're in increasing order. So I can immediately see what the minimum and maximum are. This is my minimum. And this is my maximum. So I at least know that this should be 121 and this should be 169. How do I get the median of these 20 numbers?
Average 10 and 11.
Average the numbers in spots 10 and 11. So that's number 10, and that's number 11. The number halfway between those is 143. So then, oops, Q2 must be 143. And if I want Q1, all I need to do is look at that top row, because that's the least 10 numbers out of these 20 numbers. So if I look at the top row and say, what is your median? Then it would be the average of these two. Yeah. And if I want Q3, then I will consider just the bottom row, which is the greatest 50% of the data. And their average is 154.5. Now, based on those numbers, you can make a picture of what it is with a tool called the box plot. So if I have a number line right here, then if I carefully put the appropriate tick marks, so the minimum's 121 and the maximum's 169. But put your tick marks at the tens positions. So I'll do 120 and 130 and so on, 140, and try and make a pretty good scale, 150, 160, and then when I get to 170 here, I'm done. Those are all pretty evenly spaced from each other. Then above that scale that you have drawn now is where we will draw our box plot. So at the endpoints of 121 and 169, I'll just put these dots. For each of the other three numbers, 132, 143, and 154.5, I'll put vertical lines. So here's about 132, and then 143, and then 154.5, and then you make it into a box, and you connect the whiskers, and that's actually what they're called. Sometimes you would see it referred to as a box and whisker plot. Box and whisker plot. So that's what my box plot looks like. Now, this is just a crude drawing. It looks to me that it's skewed right. Doesn't it have a tail on the right that's a little bit longer? Yeah. This would kind of correspond to a distribution that would look like this, where the tallest part of the distribution is right over the mean, and it has a little bit longer tail on the right. So I can now hopefully just pick which one of the pictures is my correct box plot. It ain't A, it ain't C, and it ain't D, just by eyeballing them. They don't look anything, you know, A doesn't look like what I drew. I don't even need to look at the numbers. A has this median scooted way over to the left inside the box. C has a box that's way too close to the lower whisker. D has a tiny little box. And furthermore, it has a maximum that's nearly 180. And a minimum that's nearly 100. So it isn't A, it isn't C, it isn't D, it must be B. And then if you wanted to, you could verify that B really does it. It has a minimum a little bit more than 120, it has a maximum a little bit less than 170. It all works out. Well, this 5-number summary stuff is easy enough when all the numbers are in order, and you can easily break it up into the lower 50%, upper 50%. However, StatCrunch will just also do it for you. You can click the box over here to open the data in StatCrunch. And we particularly want to do it on this one because the numbers aren't given to us in order. So I would open in StatCrunch. And then the 5-number summary, being that it's the minimum Q1, median, Q3, maximum, those are all summary statistics. So you go to Stats, Summary, Stats, Columns. You tell it which column your data is in, and don't click anything else but Compute, because all the stuff you want is already pre-selected. You've got your minimum, your maximum, Q1, Q3, and the median, which is Q2. So you have your 5-number summary. the minimum is 120, and Q1 is 132, and Q2, the median is 136.5. Q3 is 144, and the maximum is 150. Then they want to know which box plot is it. Well, StatCrunch will also draw you the box plot. You would go to Graph, Box Plot. We would tell it which column our data is in. It's in VAR1. Now, for some dumb reason, it wants to default to draw the box up vertically. Well, we don't want that. Click Draw Boxes Horizontally. And then compute. Okay, kind of stretch it out so you can get a picture that's not distorted. And look at how our data set must be skewed left. I can see right where the tallest part of the distribution would be. I should be able to pick my answer based on this picture. Sure does look like C. You can check it with a couple of points. That's it. All good on box plot and 5-number summary? So now let's think back to week 1, where we did frequency tables. When we did the frequency tables in week 1, we said that we had our classes in the left column, and we had the observed frequencies here next to it. And then if we wanted to, we could easily construct the relative frequency table by just taking all the frequencies and dividing by the sum of all the frequencies. Gives you a percentage. Let's make that table for this problem. It says that we have 212 female babies and 6 male babies. So, and that's all of the babies they're talking about. So there would be just the 2 classes. And there was a frequency of 6 for the first class. There was a frequency of 212 for the second class. Well, that's a total of 218. So then my relative frequency is 6 over 218 for male, and for females 212 over 218. And I could run that through my calculator and get a percentage if I wanted for those fractions, right? But the big idea is that the frequencies, I know that they add up to 218, and that the relative frequencies add up to 1. They add up to 1, which is also the number 100%. Okay, now we're going to do probability. All I got to do is scratch this word class out and write event. And I'll scratch out this word relative frequency and put probability. Super. Now it's a probability table. A relative frequency table is the same thing as a probability table. To be a probability table, you had to have each of these numbers be probabilities. And probabilities only make sense if they're between 0 and 1, or if it is 0 or 1. Where a probability of 0 would mean cannot occur. Probability of 1 is it's guaranteed to occur. And then all the numbers in between, we would interpret like as a percentage of it occurring. And this 100% down here is that if I reached into this box of 218 babies and I pulled one out, does it fit into one of these classes? And then that's 100% probability, because 6 of them were of this type and 212 were of this type, and that's all of them. Everybody's in one of those classes, according to this. So we can just interpret those relative frequencies straight away as probabilities. The probability that, so this question is not worded as good as it could be. It says the probability that a female will be born using this technique is approximately, boy, that's right on the edge of false. What they mean is, so here's what's correct. If I look at these 218 babies and randomly select one of them, what is the probability that it was labeled as a female? That probability is this number. I really can't say anything about what's going to happen with any babies except for these 218 babies. I can't be over here talking about some other baby born using this technique. That, if I wanted to do that, this would only be an approximation to that probability. In fact, answering questions like this one is what statistics is all about. I want to be able to look at my sample and then make an inference about what would happen over there to something outside of my sample. So the probability of reaching into the box of babies and pulling out one labeled female is 212 divided by 218, which is nearly 100%. It's 0.9725. They want it rounded to 3 decimal places, so it's just 0.972. It's actually 0.9724, and they want it rounded to 3 decimal places, so it's 0.972. A 97.2% chance that I would get a female baby. Then does this technique appear to be effective in improving the likelihood of having a female baby? Well, yeah, it's nearly 100, it's nearly guaranteed. It would be a rare event to have a male baby. Okay. Now, you might get a number here, or you might get a probability that's like, 0.58 or whatever. You couldn't say that would improve the likelihood of having the female baby. Even though it was bigger than 50%, it's still really close to half. You've got to be near the extremes to be able to answer this question correctly. Because why is it an issue? Because effectiveness is not well defined. We don't know what they mean by effectiveness. They could have meant that it was better than half. Well, if that was the case, then 0.51 would be effective. But that's not what they mean by effective. They mean like seriously effective. So you need a massive number up here. Nearly 1. All right, we all good on that question? No? You all right? Okay. Here's another one. 3,616 respondents say they use social networking sites, while 1,367 say they do not. So I end up with two classes, really, but now we'll call them events. These are the frequencies that I saw in this experiment, you would call it. So the corresponding probabilities, well, this totals up to 4983. So the probability that they don't use social networking is 1367 over 4983, but the probability that you do is 3616 over 4983. Question that they ask is, what is the probability that a randomly selected person from this collection of 4,983 people, which they didn't say, but you would need to say, what's the probability that they use a social networking site? Okay, it's this. As a 3-decimal approximation. So 3616 divided by 4983 to 3 decimals, 0.726. So it's like a 72.6% chance that they use social networking. Is it likely for a respondent to use social media? Yes, because the probability is far greater than 0.5. Notice that here in this problem, they gave us a definition of what likely meant. The question was, do the results suggest that it is likely for someone to use social networking? And then they've told us the definition of likely. Whereas in the previous problem, they didn't tell us what it meant to be effective. Okay. All right. Every semester, it seems that somewhere along the way, everyone forgets how to do these questions. So, make a mental note that I've told you that, and that it could happen to you. This is a probability question. They've given us what they think is a probability table over here. They want us to verify whether, or if it is a probability table, then we'll click yes, it's a probability table. Here they're calling it a distribution, whatever, same difference. If it's not, we'll have to tell them what's wrong by selecting the appropriate boxes. Then they're going to want the mean and standard deviation of the table. They don't want the mean and standard deviation of just one of these columns. That's what people do wrong. That's a totally different thing. To find the mean and standard deviation of this table, it's a special formula that I'm not even going to show you. We're just going to use a tool in StatCrunch to tell us what it is. The mean of this table would not be just adding up all these numbers and dividing by 8 or whatever people do. And it wouldn't be that for the standard deviation either. So first thing we need to do is determine if it is a probability table. To be the probability table, you had to have the 2 criteria. All of these numbers needed to be probabilities. They needed to be something between 0 and 1. And it could very well be 0 or 1. And yeah, all those are between 0 and 1, so we're good to go there. Do they add up to 1? More than likely. Let's check. Mine adds up to 1. So I will click yes. This is a probability distribution. Now they want to know the mean of this table. Here they're calling it of the random variable x. That does not, so look, if you wanted to calculate this mean, you would have to take this number times its probability, plus the 1 times its probability, plus the 2 times its probability. And it's not the funnest thing to sit there and try and calculate. I mean, you can do it. It's only got 4 rows. It's not awful. But StatCrunch will do it for us. And plus, when it comes time to the standard deviation, it's a lot more complicated. So just in the same way that I don't want you to be finding a regular standard deviation by hand. I mean, you could, but you shouldn't, because you could mess up. Open the table in StatCrunch by clicking the box. And it just imports 2 columns. One labeled X, one labeled probability of X. X is some event. Let's see, what is the event? It's the event that that they take 1 or more online courses. Right. So what I've done is I got a whole bunch of college students, whole bunch, and just put them into groups of 3 students, and then go around and poll each one of them, do you take 1 or more online courses? Which is really saying, do you take any online courses? And it could be the case that no one in the group takes an online course, or one of them could take an online course, or 2, or all 3 of them could be taking an online course. And that's what this table means. Okay. So then that makes this X represent the different possible events that could occur. And these are the only 4 events that could occur in that group of 3 people. Those are the only options. No one's taken online, or it's 1 of them, or 2 of them, or all 3. Now, this is in a weird place, the place that we go, and probably that's contributing to why people forget how to do it. You go to Stat, Calculators, Custom. It's all the way at the bottom of the list. Stat, Calculators, Custom. The values is X. The weight is the probability of X. That word weights should ring a bell, because it's like this mean is a weighted mean. It's weighted by the associated probabilities. So you get 1.572 for the mean, and you get this for the standard deviation of the table. Yeah. All right, so my mean to 1 decimal place is 1.6. And my standard deviation to 1 decimal place is 0.9. And this is the name of the game for the rest of the homework. This is all it is. Here you have big group, somehow you've gathered together a huge group of males that have this X-linked genetic disorder, and that all those males with that genetic disorder have but one child. Exactly, each one has exactly one child. Then you could do the same thing. Get 5 of them. You carve them all up into groups of 5. And within that group of 5, we could determine among these 5 people how many of you had your child inherit that genetic disorder. And then this would be all the possible cases, right? Everyone inherited it, no one inherited it, or somewhere in between. So you end up with 6 cases total, because you got to consider that 0 case. Is this a probability table? Well, yeah, that adds up to 1. Now I want to find the weighted mean and the standard deviation of the table. I click open in StatCrunch. It opens right up. Where do I go?
Stat. Calculators. Custom.
It's all the way at the bottom. Values is the first one, weights is the second one. And that's why they put them in that order, because everyone does it in this, you know. It would have been silly for them to ask for the weights first, and then the values. It would have been unnatural. And you compute. Now this mean that they're talking about here, where I told you that it's this first number times its probability plus the second number times its probability, and so on, all the way down the table. That has a more popular name called the expected value. And it's usually written as a capital E of whatever your variable is. In this case, it's an X. You can see right here, it's X. It's called a random variable because randomly, anyone in that, randomly, the solution of however many inherited it could have been any of those numbers, and we don't know which one. It's random. And it's expected value. We will have a discussion board very soon over expected value. And our interpretation here would be that that on the average, if I ever collect together 5 of these qualifying males and ask this very same question, then on the average, the response will be 2.5. That's what I'll get. Look at how this distribution is nice and it looks normal. Yeah. That really nice symmetry is unusual, first of all, but I mean, it would be, so what would be common is that it's very close, but it's be suspicious that it's perfect. Anyways, mean is 2.5, standard deviation 1.1. Now the standard deviation being 1.1 and this distribution being normal, what does that mean? Let's investigate momentarily. It means that 2.5 is right in the middle. You can see it because look, there's 2 and there's 3. And 2.5 is right in the middle. And one standard deviation away from that on either side, right? This distance from the mean over to that dashed line is 1.1, the standard deviation. And this distance here is 1.1, the standard deviation. Then that would mean this number down here is 2.5 plus 1.1, right? That's 3.6. And this number right here is 2.5 minus 1.1. So it's 1.4. According to the empirical rule, 68% of the time, the response will be between 1.4 and 3.6. Now, you can't respond with a 1.4 or a 3.6, but on the average, you can average it out and you could get something like that. Really, you could only answer 2 or 3. I think I could use this calculator. It's telling me that if you were to answer 2 or 3, that there's a 63% chance of that happening. So it's very close to the 68% rule that empirical rule gave us. It's only different here because of this being discrete. You can't actually have a situation where 1.4 people, 1.4 children inherited it. Right? It's going to be either 2 or 3, and those are the only options in this interval. If I moved over by another standard deviation, I just subtract 1.1 here, that would be 0.3. And then add 1.1 over here, that'd be 4.7. Then it would be a 1, a 2, a 3, or a 4. And the empirical rule tells us that when I go plus or minus 2 standard deviations, it should be 95%. And this little calculator would tell me if I put a 1 here and I put a 4 here, it should be pretty close to 95%. Oh, it's exactly 95%. 95%. But we already knew that from just drawing the picture. All right, question 12. Is it a probability table? Maybe. Mine is, so yes, it's a probability table. Find its mean. I'll open in StatCrunch. Stat calculators custom. Values in X, weights in P of X, compute. That's skewed left. Definitely not normal. But I know the mean to one decimal place, 2.4. 2.4. And the standard deviation to one decimal place is 1. I could play around with this calculator a little bit. What it says right now is that for whatever this problem is describing, the probability that it's 2 or smaller, the probability is about 50%. What if it was 3 or smaller? 86%. What's it going to say for 4 or smaller?
Hundred?
100%. 1. Because that's all the events. That's all the possibilities. It could have been 4 or 3 or 2 or 1 or 0. That's it. So if it's going to be 4 or smaller, it's 100%. Just the zeros, it gets 0.025, and see how that matches the entry in the table. I can change it to between and say from 1 to 1, and it gives me that entry in the table. And from 2 to 2 is that entry in the table. So evidently it's just adding up the corresponding probabilities. It says that if you want to be between 2 and 3, then you would be probability of 2 or you would be probability of 3. And if I use that word or, then you would just add these probabilities together and get 0.692. All right. Well, that's it for the homework. A sneak peek on next week. Is with that normal calculator. If I go to Stat, Calculators, Normal, it's a normal curve, right? And see how the inflection point is right over the 1? And right now, it's got half of it shaded. Half of the curve is shaded, and it stops right there at 0. It's this 0. That 0 is this 0. That's what they're talking about. The place where this shading stopped is at 0. And how much area is that? It's half the area. And if I put it to between and say, what's the area plus or minus 1 standard deviation? 68%. That's empirical rule. And if you did plus or minus 2 standard deviations, it's 95%. And if you did plus or minus 3 standard deviations, it's 99.7%. Look at how it appears that the entire curve is shaded red. That's just because it stops here at plus and minus 3. It doesn't go any further because to happen at outside of plus or minus 3 is a rare event. It's only going to happen 0.3% of the time. 0.3%. Let's see. 0.3%. Well, the 0.3 is 3 over 10. And then the percent says to divide by 100. So that's 3 out of 1,000. You'd have to do it 1,000 times before you saw it happen 3. I'd have to have a sample of 1,000, and then maybe in that sample of 1,000 there'd be 3 of those anomalies. Okay? In my sample of 1,000, I would probably find 3 cases that were more than 3 standard deviations away from the mean, is what it's saying. So it's not just rare, it's extremely rare, exceedingly rare. The gold standard is 95%. Nearly every study, anything that anybody is ever doing, more than likely, unless they have a really good reason to not do it, they're doing 95%. And we can sit here and answer all kinds of questions with this tool. What's the probability? So this bunch of symbols down here at the bottom, the P is for probability. They're saying X because they didn't want to say Z. If it was always going to be mean of 0 and a standard deviation of 1, then this would say Z, because it'd be the Z-axis. But since you can change the mean of standard deviation, they just have it as X. The probability that I witness some value, the probability I witness some Z-score less than or equal to whatever number. Well, how about minus 1.4? Okay. In a normally distributed population, the likelihood that your Z-score is less than or equal to minus 1.4, there's only an 8% chance that that's going to happen. What if we suppose for a moment that, and I'm sure it's true, but suppose that systolic blood pressure was normally distributed with a mean of 120 and a standard deviation of 18, then what's the probability that a randomly selected person has a blood pressure that's less than 140? Not 14, 140. Well, okay, it says there's basically an 87% chance that that person's BP is under 140 or equal to 140. And 120, since it's the mean, you get half the area. No shock there. And you can also do stuff like, say, 95% of people have a blood pressure lower than what number? And when I click compute, it will put that number right there because I'm insisting that it shade 95% of the area. So 95% of people is going to have a blood pressure under 150. That's how it works. And that's it. That's all I got. Are y'all done with the homework? All right. Enjoy it while it lasts, because week 5 and 6, you'll be wishing it was like this again. It gets ugly. Don't forget your midterm. It won't be quiz 3. Quiz 3 will be that normal distribution calculator stuff. And I will see y'all in a week.
Thank you, have a good one.
Bye. Don't log out.